in the last one. Like 20.
Okay, let's go ahead and get started. My goal today is just to help you feel comfortable going into that exam. And I just want to really encourage you to take that exam A seriously. I think when we took the first exam, first midterm, I saw that people very much took that first exam seriously, and they had 2 kicks at the can, both exams, and it helped. In the second midterm, it looked like a lot of us, I gotta say, we're just kind of treating that exam A as a, throwaway. And we had a whole lot of really low scores with people that took less than 25 minutes in the testing center, and that's just a waste of an opportunity. Okay, I really think, put all your effort into that A exam, and if you do well, don't take B exam. Okay, on Thursday we're going to go over that A exam, and if you got an A on it, you don't even have to come. We won't have any clicker questions on Thursday. It'll just be totally optional. Now, remember, this exam is going to be all multiple choice, and it's because of the large number of students in the class, 750, we didn't want to Xerox that many tests. So you won't be able to write on the test. You'll need to bring scratch paper, and bring enough scratch paper that you don't have to worry about wasting scratch paper. I think on that last exam, some of us were worried that we'd use up all our scratch paper, so we didn't draw free body diagrams. That was a mistake, okay? And so in this exam, I think you're going to want to use your scratch paper to make those tables for the 2-dimensional momentum problem. Because if you don't do the table, you tend to not get it right. Remember, please remember that not all of the equations that you need are going to be on the front page of that exam. The equations on those sample exams are exactly the same equations that you'll have on your exam. There won't be the equation for kinetic energy, for gravitational potential energy, for spring potential energy, for Verk, for impulse. Those will not be on the exam. Those you need to have memorized. And there's certainly nobody over at the testing center that's going to be able to give that to you there. Are there questions about the exam? Okay. Yes.
How many questions are there?
29. 29. Well, sort of. The first question and the last question are like before. You get 1 point for saying whether you're going to get an A, B, C, or D on the test. But
can we know how much will be content-wise about power?
Power will be on the exams, but not in a big way. There'll be 2 fairly straightforward questions, each worth 3 points on the exam. Well, that's both exam A and exam B. Okay, would someone be willing to give us an opening prayer today to get us started? Anyone there? Thank you.
Dear Heavenly Father, we're grateful for this day, and we're grateful for the opportunity we have to be here and learn. We ask that thou will bless us with thy spirit, that our minds might be calm and open, and please help us to learn and study this week as we take our exam, and bless Dr. Francis as well. And we are so grateful for all that we have, and we say these things in the name of Jesus Christ. Amen.
Amen. Okay, so I did that wrong.
No.
So The homework solutions and the practice tests are all at the MAC site. There are 2 review sessions that are at that YouTube channel, and one is from last fall and one is from last spring. And essentially, it's just going over those sample exams and questions about the sample exam. It's entirely multiple choice, the exam. Not all of the equations are given, and it will include the material today, but as we just pointed out in a small way, 2 questions on the exam. Just to remind us where we got to on Thursday last week, the idea of power is just how quickly you can do VERC. If Greg can do 5 billion joules of work, the question that you would ask is, how long does it take him to do that work? Okay, is that something that is going to take him a little bit of time or a lot of time? And VERC is just the amount, power is the amount of VERC you can do in 1 unit of time, the unit being 1 second. Okay, and so the operational definition looks like this: VERC divided by the number of seconds that it takes to do that VERC. Now, I've told you this before. Whenever you have a definition that's a ratio, something divided by something else, set the basement equal to 1, and that'll give you a gut level understanding of what it means. It's the amount of VERC that I can do in 1 second. That's what power means. Now, because VERC changes energy, I can also think of it as how much the energy changes, the mechanical or the total energy changes in 1 second of time. Now, there's a special case that comes up fairly often, where you're pushing something on a rough surface at a constant velocity, and you're asked how much power is being supplied by the hand. Okay, in that case, we can take that formula for VERC, force times the distance, and we can associate that displacement delta x with the time delta t, and that's just the speed. And so another formula in the special case where F is constant, 50 newtons, 50 newtons, 50 newtons, 50 newtons, and the velocity is constant, 4 meters per second, 4 meters per second, 4 meters per second. In that case, you can just multiply the 2 together to get the power. Okay? And the units of power are watts. That's a watt is 1 joule for each second. By show of hands, how many of you pay your own power bill? Good. Okay, we're adulting. Excellent. When you pay your power bill to the power company, what is it that the power company is selling you? What are you buying from the power company when you pay your power bill? Nothing? What units are you paying for? You pay for so many kilowatt hours, okay? Kilowatt hour, what is a kilowatt hour? Well, a kilowatt is just, 1,000 watts. Okay, that's what kilo means. And an hour is 3,600 seconds. Seems longer in a physics class, but that's what it is. Okay, and if I multiply that out, a kilowatt hour is 1,000 joules for each second times 3,600 seconds, and the seconds cancel out. And so what you end up with is 3,600,000 joules. It should be called the energy company. That's what you're buying when you pay your power bill. You're buying energy, okay? Now, when I was young, I thought that they were actually selling me electrons, that they were shipping in electrons to run through my lamp to make it light. Well, folks, it turns out that we have AC current in our house. That means it turns around and goes the other direction 120 times a second. And I used to think, you know, the electrons are going through those wires at the speed of light. I wasn't very smart when I was young, okay? It turns out that the electrons are moving really, really slow through those wires. And we're changing their direction 120 times a second. And so you're not buying electrons from the power company. You're just paying them to come in and shake your electrons, okay? Because they're not going very far in that 120th of a second. And so you're just paying them to come in and shake your electrons in your lamp until they get hot and light up your filament. Okay, that's not going to be on the exam. But this might, you know, what is a kilowatt hour? Now that's the amount of energy it would take to light a 100-watt bulb for 10 hours. Okay, and you would pay about 14 cents in Utah for that. Okay. Now, long ago, many, many years ago, 35, 36 years ago, I was working at Lawrence Livermore National Laboratories, which is one of our nation's premier nuclear weapons laboratories. And they have there what's called the Nova laser. At the time, it was the most powerful laser in the world. And it was comprised of 10 beam lines. These are the beam lines, and they're huge. And this room is the size of a football field, and that's a scientist. They're a little bit smaller than humans, okay? Speaking of football fields, I am so sorry about the game on Saturday. I have to accept some responsibility for that. That, it turns out, was the very first BYU football game I had watched this season, and I think I may have jinxed it. I think that was, I was cajoled into watching it with my brother, and as we watched, it was not the bonding experience that we thought it was going to be. He was yelling some things that can't be repeated. Okay, so these are the beam lines where we send the laser beam, and then we focused all 10 beams down in this target chamber. Again, those are the scientists. You see it's fairly large, but the target is not large. The target is this little tiny glass bead. The quarter's just there for a reference of size. And in that bead, we have deuterium and tritium, heavy hydrogen. And they focus these 10 laser beams all at once from different directions to create the same temperature and pressure that we have in the interior of the sun. Okay, and that causes fusion, nuclear fusion, which is what powers the sun. Essentially, that heat and that pressure cause these light atoms, deuterium and tritium, to fuse together and join together to make helium. They give off one neutron and a whole bunch of energy through Einstein's E equals mc squared equation. Okay, well, how much energy? Well, if you take 1 gallon of seawater and you extract the heavy hydrogen, the deuterium and tritium, you still have practically all of the seawater that you can surf on, okay? But just that little tiny bit of deuterium and tritium will create enough energy that's the equivalent of 600 barrels of oil. That is free energy for the whole world forever. Now, back then, I was working on this problem and proud to do so. And I would tell my parents and all of my friends that we were 20 years away from making this happen. Well, I've been out of that field for a long, long time. But when I talk to my friends who are still working on this problem, they assure me that we are just 20 years away from making this happen. And so you can see that this is kind of a slippery problem. This is a slippery problem. Now, why am I bringing this up right before the exam? Because I want to talk about the power delivered by that Nova laser. okay? That laser delivers 200 times the total power output of all the power stations of the United States. Well, where do they get that power? From Canada? From Mexico? No, they get it from Pacific Gas and Electric, okay? Now, when I look at that formula for power, it's got time in the basement. And that gives me two different ways to get a huge power. One way is to deliver a whole bunch of energy in a reasonable amount of time. But the other way is the one that is used with the Nova laser. And that's to deliver a reasonable amount of energy in a very short amount of time. If you divide by a very small number, you get a big result. And that's what they do. They, in the basement of this Nova laser building, there's a huge capacitor bay. These capacitors store energy and charge, but mostly energy. That's how I lost my hearing, remember, was the capacitor of death. Well, they trickle energy into those capacitors all day long. And then when all the capacitors are full, they dump all of that energy into the laser beam in less than a billionth of a second. And that's what gives me that very, very small denominator there. Now, I have a friend in Montana, and he and I don't see eye to eye politically. We've served in a lot of bishoprics together. His daughters were bridesmaids at my daughter's wedding, best of friends. But he would write these letters to the editor that would just make me so mad. And I would stay up all night writing letters to refute what he said. But I never sent those to the newspaper because my wife wouldn't let me, okay? So I have a hard drive filled with letters to Tom. And one of the letters, he was talking about how Montana had so many government workers, more government workers per capita than all of these other states. And so I stayed up all late at night and I wrote a letter and I said, well, it's all in the per capita, Tom. I mean, we've got one governor. California has one governor. They have 80 times more people than we have. So we have 80 times more governor per capita than California. Do we have too much governor? I mean, we've got fewer governor per cow. Anyway, I never sent that letter in, but it's the denominator there. Okay. Questions on that? Okay. So let's see if we understand it. Let's get out your clickers. Okay. A box is pushed by a hand across a level table at constant speed. The frictional force exerted by the table on the box is 20 newtons. The box moves a distance of 12 meters in 3 seconds. What's the power being supplied by the hand? With your clicker, please. Okay, last call, please. There we go. Good, good, okay. The answer is indeed 80 watts. And again, power is just the change in energy divided by the number of seconds that it takes. And that's the vec divided by the time. And the vec is the force times the distance. If I combine this together, I get the force times the velocity. And the velocity in this case is 4 meters per second times the 20 meters, the 20 newtons rather. And that gives me 80 watts. Okay, let's try another one. How many joules of work, Werk, can a 15,000 watt motor do in 20 minutes? Go. And these are the types of questions you could expect on the midterm, dealing with power.
Fast click it.
Okay, get your vote in, please. Still need a few more votes. Okay. Close enough. Good. The answer is E. Now, folks, I put this question up here just to point out that you don't always have to solve the problem. Okay? In this case, there's only one answer up there that even makes any kind of sense whatsoever. This amount of joules, that is the amount of work that this motor could do in 2 seconds. In 2 seconds, it can do 15,000 joules in 1 second, so it can do 30,000 in 2 seconds. And 20 minutes is a lot longer than 2 seconds. So everything from here on up is just silly talk. That is laughable. And so you don't have to actually get out your calculator. You just say, oh, there's only one answer up there. Okay? And that's a strategy that you can use not only in the exam, but in the MCAT that some of you are going to be taking. Now, I have here an old exam problem dealing with power. If I could get my helpers, where are my helpers? There's a helper. Any more helpers over here? Thank you. Appreciate it. Okay. Thank you. Any more helpers over here? Appreciate it. Okay. There you go.
Correct.
Meet this front row here. This front row still needs it. Okay. Raise your hand if you still need a handout.
Audio not. Try it.
Big one.
Yes.
Okay. In this problem, we have a 30-kilogram block of dry ice that's sliding down a ramp. Thank you so much. And it's dragging a brick behind. Now, the dry ice is floating on a layer of gas because it's sublime, so there's no friction on the ice. But it's a rough brick, just rough enough to keep that whole system moving down the incline at a constant velocity of 5 meters per second down the ramp. And so the first question we're asked here is to find the tension in that string. Now, anytime you're asked to find a force, that immediately suggests that you should draw a free body diagram. And so I'm going to draw a free body diagram of the simplest object, and that's going to be the ice. So I have a weight force, Earth on the ice, and that's going to be 300 newtons. I then ask, are there any magnets in this problem? No. What touches the ice? Well, I've got that string pulling with a tension force on the ice, and I have a normal force by the ramp on the ice, and that's it. And when I've got a problem like that, I always rotate my coordinate system so that the coordinate system lines up with the hill. And that means that I have to break up my weight force into its parts. I look in the direction of the normal force and I go the other way until I can take a 90-degree turn and get to the end of that weight force. And this is going to be the X part of the weight. This is going to be the Y part of the weight. This is going to be 37 degrees. And then I can say, well, this is a 3, 4, 5 triangle. This is going to be 3 times something. This is going to be 4 times something. And this is 5 times something. Well, this is 5 times 60 newtons. And so this is going to be 3 times 60 newtons, or 180 newtons. And this is going to be 4 times 80 newtons, or no, I said that wrong, 60 newtons. And that's going to be 240 newtons. Or you could say this is 300 newtons times the cosine of 37 degrees, and this is 300 newtons times the sine of 37 degrees. Whatever floats your boat. Now, once I break it up into parts, I throw away the original. And I use the fact that this is moving at a constant velocity or 0 acceleration. So this has to scream balance both in the Y direction and in the X direction. And that means that I've drawn this tension force too long, and I haven't drawn this normal force long enough. This one has to be 240 newtons, and this one has to balance this tension force by the string on the ice, has to be 180 newtons. That's old news. That's where we've been. That was so second midterm, okay? Now, part B asks us to find the power delivered by the string to the brick. Well, is the string doing positive work or negative work on the brick? Which is it? Shout it out. A mighty shout went up in the land. Shout again. Positive. It's pulling on the brick down the ramp, and the brick is moving down the ramp. The force and the displacement are in the same direction. That's positive work. And so that means it's delivering positive power. And that power, now you notice we've used P before for momentum, and I'm sorry that we're using it again for power, but I'll try to make that a different P. Okay, that's going to be force times velocity, and it's going to be positive because it's positive work being done. And so that's going to be 100, and this will be the tension by the string on the brick times the velocity of the brick. That's 180 newtons times 5 meters per second, or a positive 900 watts. Okay, every second that goes by, that string is delivering to the brick 900 joules of energy. That's what 900 watts means. Okay, now the next part, part C, is asking if the magnitude of the friction force on the brick is greater than, equal to, or less than the magnitude of the tension in the string. Well, we're being asked about a force on the brick, so let's draw a free body diagram for the brick. Well, I have a short weight force. That's only 100 newtons. And then I've got this tension force by the string on the brick. That's the other end of this string. So that's going to be 180 newtons. And then I've got a normal force by the ramp on the brick. And then I've got this kinetic friction force by the ramp on the brick. Now, wait a minute, Greg. You drew that longer than the tension force. If we have zero acceleration, and we do, shouldn't this balance the tension force? Oh no, because when I break up this weight force, it has a y part and an x part. And if this has zero acceleration, this one force up the ramp has to balance both of these forces down the ramp. And so that means that this friction force, kinetic friction force by the ramp on the block, has to equal both the tension by the string on the block plus the x part of the weight. Now, since this is 100 newtons and this is 37 degrees, this is going to be 60 newtons, this is going to be 80 newtons, this is going to be 80 newtons, and this is going to be 180 plus 60, or 240 newtons. And you can see that that's bigger than 180. Okay. How are we doing so far? Other questions? Okay, let's go to part D. Is the mechanical energy of the earth ice system conserved as the ice and the brick move down the incline at constant speed? Well, remember, mechanical energy or total mechanical energy, depending on what you're calling it in that day, is just the sum of the kinetic energy plus any potential energy we have in the problem. Well, there's no springs in this problem, so we don't have to worry about that bucket. Well, it's moving, the ice is moving at a constant velocity, and so the kinetic energy is conserved. In other words, it stays the same. But the gravitational potential energy, as the ice gets closer to the center of the earth, my potential energy is decreasing. And so this term is getting smaller. And that means that the sum of those is going to be getting smaller. So the answer is no. The total energy of the system is draining. Well, how's that happening? Well, this force here is doing negative, Eric, on the ice. Okay, it's pulling up the ramp while the ice is moving down the ramp. Okay, and we're asked, find the power that is supplied by the string to the block of dry ice. Well, in that case, I have power is equal to force times velocity, but minus, because the Verk is negative. And so here I'm going to have minus 180 newtons times my 5 meters per second, and that's going to give me a negative 900 watts. So what's happening here is that every second that goes by, the string is stealing 900 joules of energy from the ice and giving it to the brick. Now, the only reason that the brick doesn't get more energy is because the friction force is stealing energy from the brick, and it's stealing more energy each second than the string is giving to the brick. So the system is losing energy all around due to that friction force. See if your neighbor is on the bus with that. See if your neighbor is on the bus.
Ice is friction. Ice. That does not, brick has friction.
Tell me what you.
How are we doing? Are we okay? Questions? Okay.
That one is a negative. But.
Let's, let's practice what we've learned in the course so far by answering this question. How many different ways can you find, using what we've learned in the course so far, to measure the muzzle velocity of a bullet? In other words, if I fire a bullet, I want to know how fast is it going when it leaves the barrel. With your neighbor, try to come up with as many creative ways using the physics that we have talked about in this class, using the ideas that we have discovered to measure this velocity. Talk to your neighbor.
Fired into a vacuum. Shoot it out. Spring in it, spring. What the energy would have been. The back to rifle. That energy is same method, it's like spring. I was back to top.
Okay, I'm just going to race through some ways, and hopefully you have thought of some of these ways that I'm going to talk about. Plan A is just to use a radar gun, and you know, that's just something we haven't learned about in this class, so we're gonna throw that one away. But before we do, I found this picture on the internet, and I just want to point out that some jobs are worse than others. That is not a good job there. Okay. One technique we could use goes way back to the beginning of the course. We know that if you fire a bullet in a horizontal fashion, it's going to travel in this parabolic path. And we can use the kinematic equations to describe that path. Now, if we were to measure the distance it goes before it lands and the time that it takes, that would give us, if we divided by that distance by that time, that would give us the muzzle velocity. Because remember, the horizontal velocity doesn't change as time goes on if you ignore air resistance, which is kind of a sketchy thing to do with a bullet, okay? But we do it anyway. Now, if we don't want to use a watch, instead we could just measure the height of that barrel. And then we could use our formula that would tell us how many seconds it flies through the air before it drops a distance h. And then if we solve that for t, we could then solve the original equation for velocity, okay? So just using the kinematic equations, we could measure this. But let's talk about ways that we could use the ideas of energy and momentum that will be on this exam, okay? Well, first of all, let's look at energy. One way is to just take that gun and fire it straight up. And, you know, if you're at FBI and you're trying to find the muzzle velocity of a gun, you could just lean out your second story window and fire it straight up and have your partner kind of go up to the 20th floor and look out the window and, you know, carefully and see how high it goes. Now, if we call this height 0, then we're going to start with just kinetic energy by definition of where we put our height 0. Now that bullet has to stop to turn around and come back down. So up there, it's all going to be gravitational potential energy. And if we make the assumption that we don't have to worry about air resistance, again, not a perfect way of thinking of things, but it simplifies the problem. Then we have energy conservation, and I just set the kinetic energy at the beginning to the potential energy at the top. I cancel the mass, and I get this formula that will give me that muzzle velocity. Okay, so pretty straightforward, just balancing the energy. But that's not the way they do it down at FBI headquarters. They do it something more similar to this, where we fire the gun into a block and we let it slide across some rough surface. Okay. Now, in that collision between the bullet and the block, what's conserved? Energy or momentum? Momentum, yeah, that is a maximally inelastic collision. That does not conserve energy, but it does conserve momentum. Now, if I can measure the distance that it slides and also measure the friction that it experiences on the table, I can find that muzzle velocity. The first thing I do is during the collision, I conserve momentum. And here, I use the fact that before the collision, it's just the bullet that's traveling at this velocity I'm looking for. After the collision, that equal sign is the collision, both the block and the bullet are moving together. So I treat them as one unit, moving at some V block. Now, if I could find V block, I could find the muzzle velocity because I know the mass of the bullet, I know the mass of the block, okay? So if I know how far it slides, is that an energy problem or a momentum problem? Yeah, how far, that's energy, okay? So I use the energy formula. The energy in the morning is equal to the energy at night, except when it's not. And here, initially, I have kinetic energy of the block and the bullet moving at this speed here, and I've got to have 1/2 mv squared. And then the friction on the table does negative Verk, and I get the kinetic energy down to 0. And so if I measure the friction, I measure the distance, I know these guys, I can find this velocity, I plug that in there, and I can find the muzzle velocity. Does that make sense? It's a two-step process. Now, again, I said this is something like what they do, but not what they do. What they do is what's called the ballistic pendulum, where they fire that bullet into a block that's hanging from some pendulum, and they essentially look to see how high the block swings up before it stops and turns around. And so in that case, we have a maximally inelastic collision, like in the last scenario. And this time, because the string does no Verk, a Tarzan swing does no Verk, the kinetic energy right after the collision is going to be turned into potential energy when it turns around at the top of the swing. So just by knowing how high it goes, you could find that velocity. See if your neighbor followed those different ways of measuring the muzzle velocity. So let's review for exam 3. I just want to make sure that everyone understands the 3 different flavors of collision: elastic, inelastic, and maximally inelastic. In all 3 of those flavors, momentum is conserved. There's no such thing as any collision that doesn't conserve momentum, even if it's an explosion involving C4 explosives, as messy as you can imagine. Now, it's the energy that determines whether something is elastic, inelastic, or maximally inelastic. Maximally inelastic is easy to recognize. They stick together and they're moving together after the collision. You can see that. That's obvious, okay? And that's going to be the easiest question on the midterm. Oh yeah, that's maximally inelastic, okay? What's hard is when you're trying to decide between elastic and inelastic, because there's nothing you can see visually that will tip you off which it is. You can't sniff the air and say, oh, inelastic. Yeah. No, you have to do a calculation. You have to calculate the energy before the collision, right before the collision, and you have to calculate the energy after the collision, right after the collision. And if you get the same number, that's an elastic collision. If you get a different number, that's inelastic. But you have to do we have to do 2 calculations, okay? So be careful on that in the exam. You know that in the homework, there was a problem where you were asked, is it elastic, inelastic, and maximally inelastic? And I think a lot of us got that wrong because we said, oh, it didn't stick together, so it's not maximally inelastic. And Greg said elastic hardly ever happens. So you chose inelastic. And that was wrong because Greg had worked really, really hard on the numbers to make that an elastic collision because I'm evil. Okay. Yeah. Let that be a lesson to you. Okay. He's evil. 3 or 4 times, 4 times to be exact, you're going to have to solve a basic collision problem on that exam. And that's just where I give you the masses and velocities of 2 blocks that collide with each other. And after the collision, I only give you one of the velocities and I ask you for the other. Now you should be able to solve these problems really, really quick because there's a lot of them, okay? And the way you do it is you just look at the momentum. And it's not important that this have 32 franci. It's not important that this have negative 48. This is not going to stay the same, and this is not going to stay the same. What is important is that when I add 32 to negative 48, I get negative 16. The total momentum for the 2-block system is negative 16 franci. And that's what stays the same. That's what has to still be negative 16 after the collision. And if this block has 3 times 4 or negative 12 franci, well, to make the total negative 16, this big block has to have a momentum of negative 4. You see where I'm going with that? Now, how fast does this have to go in order to give me a momentum of negative 4? Well, first of all, it has to be going to the left, and the velocity is just going to be the momentum divided by the mass, and so that's going to give me 1/3 meters per second to the left. Or I could say negative 1/3 meters per second. What I can't say is negative 1/3 meter per second left, because that's 1/3 meter per second right. Negative left is right. Okay. Also, 3 lefts make a right, if you remember from driver's ed. Okay. Questions on this? Now I can dance this different ways. I can give you both of these final velocities and only one of the initial velocities and ask you, how fast and in what direction was the blue block going before the collision? I could dance it that way. The other way I could dance it is to say, well, what if they stick? What if they stick? How fast are they going after they stick? Well, I still have negative 16 Franci. I didn't change anything up here. And that means I still must have negative 16 Franci down here. And since these two together have a combined mass of 16 kilograms, that means they must be going 1 meter per second to the left, because 16 times 1 is 16 Franci to the left. Okay? See if your neighbor is going to be able to work those 4 problems on the exam without even breaking a sweat.
Have you taken the exam?
That's negative.
Okay. Another problem that you'll see several times on the exam, and this is actually 2 problems, is illustrated here. A 500 kilogram car is moving at 20 meter per second when it hits its brakes and slides across the pavement, level road. If the coefficient of kinetic friction is 0.5, I can ask you how far it will slide before it stops. I can also ask you for how many seconds will it slide before it stops. If I ask you how far it will slide before it stops, that's an energy problem, okay? And so you would immediately go to your Werk energy equation. That's the starting point for every, not just some, every energy problem starts right here. Now, because you're on a level road that we can call height 0, and there's no springs in this problem, by energy we mean kinetic energy. And so my initial kinetic energy would just be 1/2 mv squared. And then the friction does negative Werk, negative because the car's going one way and the friction is acting the opposite way. That's negative Werk. And then the car stops, so there's no kinetic energy. Well, I know the mass, 500, I know the V, 20, and so that gives me 100,000 joules. I can quickly find the friction force. With 500 kilograms, the weight is going to be 5,000 newtons. The normal by the road is going to balance that at 5,000 newtons. And that means that the friction is going to be 1/2 of that, because it's mu times n. So that's going to be 2,500. When I solve that for delta x, I get 40 meters. Now, if I want to know how many seconds it slides before it stops, that's a momentum problem. And the general momentum equation is that the momentum in the morning is equal to the momentum at night, except when it's not. And it's not when there's an impulse, which is a force times a time. Now, in this case, the momentum is mass times velocity, and then when it stops, it's 0. Now, in this case, that minus sign comes from the fact that this is a vector equation. And if we're calling the momentum that I start with positive, the friction is going to be fighting that. It's going to be in the negative direction. Okay? Now, the mass times the velocity is 500 times 20, or 10,000 Franci. The friction's still the same. It doesn't matter which problem you're solving. Friction is friction. And when I solve that for time, I get 4 seconds. Now, wait a minute, Greg. It stops in 40 meters, but it takes 4 seconds. 4 meters, or 40 meters divided by 4 seconds is 10 meters per second, not 20 meters per second. What happened? Well, the car's only going 20 meters per second when it first slams on the brakes, and then it slows down to 0. To see how far it gets down the road, I don't want the fastest speed of 20. I don't want the slowest speed of 0. I want the average speed halfway in between, which would be 10 meters per second. So in 4 seconds, it travels 40 meters down the road. Check on your neighbor once again. Okay, are there questions on that? Again, you're going to see that several times this week. If you turn that page over that we handed out, there's an old exam question, a two-dimensional collision problem, and we're going to solve that. You've got a car, 300-kilogram car moving at 18 meters per second east, and it collides with a 600-kilogram SUV, truck, going 12 meters per second, and they lock bumpers and become one ugly-looking vehicle with 8 wheels. And so we're going to solve this problem as an example. So why don't you try to solve part A while I erase the board? Work with your neighbor. Okay. Now, in this problem, we're first asked to find the total momentum of the two-vehicle system just before the collision. Now, if I look at I just want to point out that the most important step in solving one of these two-dimensional momentum problems is always going to be that line right there, separating out the X part of the problem from the Y part of the problem, where I'm using a standard coordinate system. And so for the car, it's all in the positive X direction. And 300 times 18, that's going to be 5,400 franci, okay? And none of that's in the Y direction. For the truck, does everyone see where I got the 5,400? Is that straightforward? Just 300 times 18, plug into the calculator, okay? For the truck, it's all in the positive Y direction, and it would be 600 times 12, or 7,200. Now, I wish I had a happier story to tell. But when this was on the exam, a lot of people in the class gave the answer for part A as the momentum total is equal to the momentum of the car plus the momentum of the truck. That's equal to 5,400 franci plus 7,200 franci is equal to 12,600 franci. Wrong or sick and wrong? Yeah, that's sick and wrong. That would work with energy, but that doesn't work with momentum because this is a vector equation. Okay, and so what we have to do is we have to add these as vectors. So I add up the two columns and my P total is going to have an X part of 5,400 and a Y part of 7,200 Franci. So let's draw that. My X part is going to be 5,400. My Y part is going to be 7,200. And my total is going to be this vector here. And the magnitude of that vector is going to be given by Pythagorean theorem. That's going to be 7,200 squared plus 5,400 squared square root. And that's equal to 9,000 Franci. This angle here is going to be equal to the inverse tangent of 7,200, the opposite side, over 5,400, the adjacent side. And wouldn't you know it, that's 53 degrees. Who saw that coming? Okay. And this is a 3, 4, 5 triangle. This is 3 times 1,800. This is 4 times 1,800. And this is 5 times 1,800 Franci. Okay. So if I were giving my answer, I would say that the P total is equal to 9,000 Franci at 53 degrees north of east. That would be the answer. Now, part B is really, really simple. What's the total momentum, magnitude, and direction after the collision? Well, for part B, all I have to say is that the momentum total after the collision is equal to the momentum total before the collision is equal to 9,000 Franci at 53 degrees north of east. Okay, why? Because momentum of the system is conserved. Now, if I want to find the velocity of the mangled 2-in-1 vehicle just after the collision, normally the total momentum is equal to the mass of the car times the velocity of the car plus the mass of the truck times the velocity of the truck. But in the case where they're moving together, this velocity is the same as that velocity. And so I can write this, I take the velocity out and collect my terms, the mass of the car plus the mass of the truck, or I can write this as the mass total times the velocity, okay? And so for part C, I can say the final velocity is going to be 9,000 Franci at 53 degrees north of east, divided by the total mass. 600 plus 300 is 900 kilograms, and that's going to give me 10 meters per second at 53 degrees north of east. Now I can only do that, divide the total momentum by the total mass, if they're moving together. If they're moving together. Okay. Now we're asked to find the kinetic energy of the mangled 2-in-1. Well, that's just plug and chug. Okay. The kinetic energy right after is going to be 1/2 times the mass, 900 kilograms, times the velocity, which we said was, actually, we want the speed, 10 meters per second, and we square that, and we get 45,000 joules. Now, the last part asks us, if the coefficient of kinetic friction between the mangled vehicles and the road is 0.35, how far will it slide before coming to rest? Well, we just saw that problem, didn't we? We can do that over here. That's an energy problem. And we're going to have 45,000 joules. And then we're not. And that's because a kinetic friction force is acting over some distance. So if I know this kinetic friction force by the road on the system, I could solve this. Well, I have a weight force that's equal to 9,000 newtons. I have a normal force by the road on the system that's 9,000 newtons. And this friction force is going to be the coefficient times the normal force. That's going to be 0.35 times 9,000. And that turns out to be 3150. And so if I plug that in here, and solve for X, I get an answer that none of us care about, okay? Because this is an R exam. Check on your neighbor, please. Are there questions?
No.
Yes, sir.
Work. There. Must be negative.
What?
45,000 joule plus negative.
Oh, if this question was on your exam, it would matter to you. I'm just saying it doesn't matter to us because, oh, yeah. Right. I mean, you will solve this problem on the exam, just not with these numbers. So whatever number that turns out to be is not going to be something that's going to make your life better. Okay? Okay. I also would like to point out that there will be an energy problem on this exam. Now, this energy problem was on one of the sample exams, and the detailed solution is there at the MAC site. It also happens to be one of the problems that is in your homework, and the reason for that is that I really love this problem. This is the quintessential energy problem. It's got it all. Okay, it's got gravitational energy here and here. It's got kinetic energy there. We've got positive Werk done by the hand. We've got negative Werk done by the friction. We've got spring energy over here. It's all there. Plus, it has a bowl. And you know that most of the energy problems have involved either a bowl or a hill or a loop-to-loop. And that's because with those types of surfaces, we can go back and review centripetal motion. And so if I were to ask you for the normal force at point C, you better get an answer that's bigger than the weight of the block. Why? Because the acceleration at block C, centripetal, points up towards the center. And so your free body diagram had better scream up in the direction of that acceleration. Okay, if you're dealing with a hill, you're going over a hill. In that case, the centripetal acceleration points down towards the center of the circle. And in that case, the normal force is going to be smaller than the weight. Okay, we don't have time to work through this problem, but I would encourage you to go through the solution carefully, because this is the type of problem you're going to need to solve on your exam. Okay, good luck, folks. May the net force be with you. And remember, I love you no matter how it turns out. See ya.